Hello everyone. In today's video, I'm going to be covering a couple more reactions just in case that these are also covered on your exam. Um, these will be the first couple reactions on page 8. Now, I don't think she will cover everything that is on page 8, but just in case she does cover some of this stuff, I'm going to cover it in this video. So to show you specifically which things I'm talking about, I'm going to be covering these. Okay, so these highlighted ones right here. So I'm going to cover the formation of cyanohydrins, the addition of primary amines, the addition of secondary amines, and the Wolff-Kishner reaction. All right. So hopefully, after this should cover everything that should be on your exam. So let's just jump right into it. All right. So now for the first reaction, aldehydes and ketones. Use of aldehydes and ketones in the formation of cyanohydrins. So cyanohydrin is this structure right here. We have a carbon, we have a cyano group and an alcohol group on the same carbon, and it's made from a aldehyde or ketone. And really, I think it's pretty self-explanatory how this works. You have a nucleophilic, Cn minus. We've known from before that this is a strong nucleophile, and this can come and it will attack the electrophile right here, and it'll go up, right? Same thing for here. This will go up, and then you have the addition of the CN group, and then you have an O minus, and then all that remains is the protonation step. So this or this. So I think either condition here is acceptable. You can have NaCNH plus or CnHCN. I think you will see both. And it says here aldehydes or unhindered ketones. So both of these are aldehydes, but you can use ketones, and I guess just as long as they're not, some bulky group over here. And so as long as it's not bulky. Uh, but yeah, this is a pretty straightforward, simple reaction, and it shouldn't be too much of an issue. All right, so moving on. This next reaction, we're going to be doing aldehyde and ketones used in the formation of what we call a imine. Okay, so we're going to create an imine, and we're going to use aldehydes and ketones in the presence of a primary amine and H plus to form an imine. All right, so this is done in the condition of H plus. Now, some of you might ask, does it matter if I use H plus or H3O plus? Well, that's something we're going to talk about, and something that's going to be very important. Okay, so in these later reactions, as we go towards test 3, it's going to be very important for us to understand the effect of introducing aqueous and non-aqueous conditions. Right now, I'm having acidic conditions, but it's non-aqueous. So there's no water. But then if I, obviously as the reaction progresses, it will slowly become more aqueous. You'll see. But it's very important that we do this in non-aqueous conditions, and you'll see why. And that the majority of this is occurring in non-aqueous conditions. So what happens is this reaction progresses using a ketone or aldehyde. That's why there's no groups up here, ketone or aldehyde. And we use a primary amine, and I'll explain what primary amine is. Hate this font. I don't know why it's the standard font, but it forms what we call an imine, right? And this is the imine, right? So imine is this formation where you have a carbon double bond N, and then you have your R group, right? And so what a primary amine is, right? So primary amine is a nitrogen group that has a single group on it. So yes, it's typically R group, but it can be other groups as well. So might be another nitrogen, or it might be something of that nature. So it doesn't necessarily have to be an R group, but usually for most of our cases it's an R group. So one R group and two hydrogens, right? A nitrogen needs three sigma bonds, right, and one lone pair to be neutral. So this is a primary amine, and so there's a special reaction that occurs when I have these conditions. When I use a primary amine, there's a different reaction when I use a secondary amine. So two R groups, and we'll look at that next. Okay. So the first thing that happens, right? What happens is the lone pairs on the carbonyl oxygen get protonated. I mean, the oxygen gets protonated using one of its lone pairs. And so the purpose of this is that this activates the carbonyl structure, right? And so, all right, so I'm just going to copy and paste. So this activates the carbonyl structure, right? And now we have a positive charge. Okay? And so now that I have that positive charge, now this is activated and this is more electrophilic. This is more partially positive now because the oxygen is now pulling a lot more, right? My dipole moment is greater. You've seen this before, and we do this a lot, right? To make things better electrophiles. So now the nitrogen is going to be able to attack, right? And now that it can attack, okay, so what we get now, right? So what we get now, fill in some things, right? So this has a hydrogen on it. Draw that, right? So this comes up, and this will go over here, right? So now this will have two lone pairs again. And now the nitrogen, right, use one of its lone pairs to attach at this location, right? So that makes this nitrogen positive, okay? So what happens after this step? So after this step, we always go towards stability. Each time we're going to go towards stability, right? And so now I have a positive charge. What happens? Well, okay, I used one of the lone pairs to attack here. So what's going to happen is I'm going to deprotonate that nitrogen, right? And I know I said that this is non-aqueous, but immediately as this starts progressing, there's going to always be a little bit of aqueous, but just as long as predominantly it's not aqueous, that's all that matters. And so what happens is we have H2O here, okay? And so this H2O is going to come and deprotonate this, okay? And this nitrogen will get a pair of electrons back. So we'll get its pair of electrons back, and we'll get this nice structure, okay? And so now everything is neutral again. So what do I do? Okay, so we need to remember what our goal is, right? So our goal is what we've done is remove the oxygen, and now we have this nitrogen group. So the oxygen needs to go away. And so how do I make it go away? I need to make it a good leaving group. So what I do essentially is we're going to be protonating it, right? And so I have H plus. So now everything is neutral in the molecule, and so now I'm just going to be protonating, okay? And so now, right, difference is this has another hydrogen. Now this is positively charged. And now that it's positively charged, the nitrogen, this oxygen, it's water now, is a good leaving group. And so water is a very good leaving group. The oxygen is positive. It's pulling on the bonds a lot. It's ready to leave. It can leave. And so to help it leave, okay, the nitrogen, with one of its lone pairs, contributes one of its lone pairs to form a double bond to help stabilize the carbon, right? Because the carbon, it can't be, it's stable as a carbocation, and you could do this as a two-step or a single step, right? Right now I'm doing it as a single-step process where I show the nitrogen contributing a lone pair to form a double bond, and then the oxygen leaving. But I could also make the oxygen leave in this case because the carbocation, secondary carbocation, is unstable, but it's not as unstable as a primary. So we're allowed to form secondary carbocations, just like we've seen in SN1. And so the result is this. Here's what we get. Okay, so look at it with me. So I've just flipped this back to make it look nice, right? I could have put it down here, but I don't like how that looks. So this oxygen leaves, and I'm left with my structure right here. So my structure, okay, so here's the backbone, the carbon backbone here, and the nitrogen with its one R group and its one hydrogen. Now it has a double bond now. And because it's a double bond and because it's lost its lone pair, it's now positively charged. So it has a total of 4 bonds now, and that's the the positive charge of nitrogen. And so what do we do next? Well, what we do is very simple, right? And at this point, we have a positive nitrogen, we have a hydrogen on it. So all that happens is we deprotonate. And so, okay, and so we have H2O, and voila, okay, and that's it. Where did I paste this? Paste it on top of it. All right, so here you go. So this is the Imine, right? So this is the Imine, and one thing to note is that realistically, all these reactions are double two arrows, right? One going in one direction, the other one going in the opposite direction. And this is because that these are all reversible. This whole reaction is reversible. And so what I mean by that is that, in the end, of course, we produce H3O plus. And so if I want to do this the other direction, right, H3O plus this, it will go in this direction and will go in the reverse, and I'll eventually get back the ketone or the aldehyde, whatever I started with. So you need to understand that these are reversible. Okay, so I change this ugly font. Okay, so a lot of these reactions will be reversible if we introduce aqueous conditions, and that's why in the beginning we have to do this H plus, not H3O plus, because if I did, the reaction would not progress. I have to have it in non-aqueous conditions. Okay, there's always going to be some water, but this is water helps facilitate as a weak nucleophile and to help progress this reaction. But if I have large amounts of HCl plus that do begin to form, that it does begin to form. So as we're making this more and more HCl plus is forming, and we'll start going towards equilibrium where we get some parts this and some parts this. Okay. So yeah, that's imine formation. Now let's look at secondary amines and enamine formation. All right, so here we have the ketone. All right, I'm just gonna keep using ketones. And then we have a secondary amine, right? And I've essentially drawn the structure of the molecule they have here. And don't let this H3O plus confuse you. This is the reverse they're showing, but this still has to occur in H plus. So this is missing. So it has to be H plus. Okay, it works the very same way. And so the first step is the protonation step, right? Just as before. Right? Almost all of this is going to be the same. So, but don't just skip ahead a little bit. All right. So now I have this protonated, right? And just as before, now that it's activated, right? I come with these lone pairs and I can attack, right? And then can give these back to the oxygen. There's a bad arrow. Another bad arrow. All right, decent. Okay, so now the next step is we're going to show this this attachment. Okay, so we have this now, and so now the oxygen is no longer positive, but the nitrogen is positive, right? And then we're going to use H2O, its lone pairs, deprotonate, and give the nitrogen a pair of electrons, right? And then we have this now, okay? And so now we have this with its lone pairs, and then so you know what happens next, right? In the presence of H plus, right? Because we're still doing this in acidic conditions, and so then oxygen gets protonated again because we want to get rid of the oxygen. So this is the direction that we're going in, right? Okay, and so now we have this. Draw those charges. We have water formed now, and so now this is the tricky part. Okay, so what happens now is this. All right, so here's the tricky part. So the same thing as before, nitrogen with its lone pair is going to contribute that lone pair to attach, right? To form a double bond, and it's going to help the oxygen to leave, right? And so here's the part that it makes this different, okay? The difference is that the nitrogen no longer has another pair of hydrogens, right? It's just now it's carbon groups, and you can't really do much with carbon. You can't deprotonate a carbon group and give the nitrogen a lone pair again. We can't do that. So what we have to do is what you'll see. Okay, so what we have now is this, right? And so this now is positively charged, though. Okay, so I've eliminated the water, but my nitrogen is still positively charged. So the issue with that is that my molecule isn't fully stable yet. And so what happens is we're going to have an E1 reaction. Okay? And you'll be like, what? Why is E1 happening now all of a sudden? Well, E1 is going to happen because we have you can kind of look at it like this, where you can essentially think of this as a one-step process, and this OH leaves, and I'm introducing kind of a carbocation right here, right? And carbocations, are the places where we perform SN1 and E1. And, I have the structure currently, but it's not stable. So I can perform E1 to form a double bond that will, allow the nitrogen, will kick up this double bond back and form a lone pair of nitrogen again, stabilize it, all the while stabilizing the deficiency of electrons for the carbon. So what we do is we have to take the most substituted side, right? So I have this side and I have this side of the molecule. And obviously these have hydrogens, this has hydrogens. And so I have to look at the side that will form the more sub double bond, right? We have to follow Zaitsev's rule here. And so this side is going to perform E1, right? So water is going to come and it's going to act, E1 uses a weak nucleophile, weak base, right? I mean, the weak base, not weak nucleophile. And this will form a double bond right here. Right. I hope everyone can see how this is more sub than this side. This side will form a monosub. This side forms a, disub. And so this will kick these electrons back up to the nitrogen. Okay, so let's see what that looks like. All right, so this is what this looks like. Okay, and so now I've formed this, and now the nitrogen is neutral, and now I have stabilized my structure. So this is the formation of what we call the enamine, right? So this is the enamine. Okay, and it's always going to be the most sub double bond. All right, and so we have the attachment of the secondary amine, and we have the formation of the double bond. So pretty simple, and just as before, right? We go in the reverse direction. All these have the reverse direction. Okay, all of them have the reverse direction. All right. So not too bad, not too bad. Very cool, and I think it's pretty straightforward. Just a bit of mechanism involved. All right. So now let's look at Wolff Krishner. All right. So now I'm going to show you guys Wolff Kishner. So what Wolff Kishner is essentially is a reaction used to reduce carbonyls. I believe aldehydes and ketones. Particularly, I'm not sure about other ones, but it's specifically for aldehydes and ketones. Okay, and so not other ones. Okay, and so this reaction, what I want you to think of is, so we use NH2, NH2, KOH, and DMSO. This is just the, DMSO is the aprotic solvent. And so what this functions as is it's basically has the same mechanism as a primary amine. So if you go back to the primary amine mechanism in the presence of a ketone or aldehyde, we get the imine. And so, like I said before, it doesn't necessarily always have to be an R group. In this case, it's another NH2 group that is bonded to, a primary amine, two hydrogens and one group. And so this is, the result. So we have this nitrogen, it's in the imine, right? This structure here is the imine, and now it's bonded to its other group that was there, which is the NH2. And so here's where the reaction gets juicy. Okay, so we don't. This is not done in H plus. Really, you don't have H plus here. I think we use the OH minus to propagate this and make this a better nucleophile. Whatever, it's not very important. What's done in the book. I believe they have H plus here, but obviously you don't have that in the reaction. It's not going to be on the exam arrows or whatever. But anyways, all you need to know is this is the first step. The first step forms a structure that you should understand how it forms. It's the same mechanism, just the R group or the group that's on the nitrogen is different. So at this point, here's where it's the juicy part. Okay, so the juicy part is the use of the OH. Damn, I'm really gonna use this font. All right, so we're gonna use the OH minus, right? KOH minus, and use one of these lone pairs to come and deprotonate one of these hydrogens on this nitrogen. Okay, so I'm doing this in basic conditions, right? And it's going to deprotonate, this acidic molecule right here. All right, and so what that's going to give us, it's going to give us, a transition state. All right, and the transition state is going to look like this. All right, so here's our transition state. So this gets deprotonated, nitrogen gets a negative charge, right? And so we have one form where we have the nitrogen, right? We have the nitrogen like this with a negative charge, and we have the imine, and then we have the form where this goes, and this one of these is going to resonate. It's going to form this double bond right here, and this is going to come down, right? And so this is the two structures here that we get. And so what happens at this point, right? We go from this structure, and I take H2O, right? Because now I formed a pretty strong a base right here, right? A C minus is very unstable and very basic. So this is going to abstract a proton from water. Okay, and so this is going to form the next. So what this form is basically just this guy, just very it's protonated, and it's nothing on that carbon. Now we have a neutral molecule again, and so essentially what we do is just we repeat the steps again, and we get another step with our strong base, right? And we're going to protonate, and this is going to give this nitrogen again another negative charge, right? And this time I'm not going to show all the resonance structures, but we'll take a look at what it forms. Okay, so this one's going to just form this. I have a negative charge in here. I figured out how to do it in the program. This has two lone pairs on it now, right? So it's negative. And so what happens is this is just going to resonate inwards, right, to stabilize that. Okay, but now to make this work properly, right? Right? So what happens is this is going to resonate in, and this bond is going to break, and it's going to be given to this carbon here. Okay, so this nitrogen is now going to break, and these nitrogens are going to be three bonds, triple bond to each other, and this is going to bubble out as N2 gas. Right? So now what we have is the structure right here. Okay, and so this structure now has just a negative charge on it, right? We have a carbon, a carbanion, and so this is like a very strong base. And so what this is going to do, it's going to take any hydrogen from from water. Water is the most easiest source of these hydrogens. So it's going to take this hydrogen away, and it's going to we're going to get a normal alkane or alkene or whatever that this was on the structure before. We're going to get this. So we're going to get the fully reduced structure. And so basically the difference we have is the complete removal of the carbonyl. And so this is now gone, but we had to go through these steps to get there. And so this is the Wolff-Kishner reaction. And what this is good for, right? So we have some rules. We have to avoid halogens and other good leaving groups, right? Because we're dealing with, something that will be nucleophilic. We're dealing with nucleophilic things in the process of this. God damn it. Sorry. In the process of this reaction. And the main thing that this is important for is, so if I'm just going to scroll up on the reaction sheet. If I scroll up on the reaction sheet, let me find it wherever it is. Right here. Okay, so before we've been using Clemmensen reduction as a way to remove carbonyls from aldehydes and ketones. And what this says is avoid using reactant in the presence of alkenes, alkynes, alcohols, and amines. So that gives us some trouble sometimes. If I can't do this in the presence of all these things, that's a lot of times I have these things on molecules. I have alkynes, alkenes, alcohols, whatever. Especially in synthesis, I'll have those present. But sometimes I need to reduce my my carbonyl structure. So the solution to this is Wolff-Kishner. So you're going to use Clemmensen reduction and Wolff-Kishner reduction interchangeably, depending on the situation. So if you have a situation where you have alcohol and you have a carbonyl, but you need to get rid of the carbonyl, but you have alcohol, you use Wolff-Kishner. And you'll use them interchangeably in this way. So depending on the conditions. This gives you another way to reduce. Okay? And so I think that should be all the reactions. Let me make sure and check. Yeah, so that should be all the new reactions that you need to know. So I hope you guys are practicing these because really I don't want you guys to take this test lightly. All right? So do your best and good luck. Hope this helps.